wabarakatuh to Dr. Waizun. My name is Muhammad Zuhilmi and I would like to explain and make an elaboration about the turbo machinery article that I have found. The title for the article is a comparative study of optimization methods for aerodynamic design of turbo machinery blades. The article was published on 8 May 2000 at Munich, Germany, and the author for this article is Dr. Shahrukh Shahbal. For the introduction, the designing turbo machinery is a difficult attempt that requires solving complicated problems with the highest accuracy in ever-declining timescale. Another major industry where it is become more difficult for designers to innovate is turbo machinery design. As a result, the scientific community has seen a rise in the development and application of optimization techniques. However, the most documented optimization method, particularly heuristic technique, like the genetic algorithm, have not succeeded in become crucial tool in the aerodynamic design of turbo machinery blade, despite their demonstrated utility. One of the primary causes is the unacceptability high computational cost associated with various optimization approach when used with a highly nonlinear complicated cost function, like that found in a turbulent viscous flow. The second is a widespread misconception that optimizers typically produce useless design idea instead of identifying weak place in a design system. This article basically proposes a novel approach that allows for the every effective use of many optimization techniques, includes stochastic ones, enabling the generation of designs in a reasonable amount of time. A very quick alternative flow solution that accurately depicts the physics of the viscous tree has been created by taking advantage of the linearity of the flow response to various geometrical disturbance without having to fully solve the Reynolds average Navier-Stokes equation for the entire dimensionless flow field. The code can be executed in a matter of seconds as opposed to a complete Navier-Stokes calculation, which takes many hours. As a result, the optimizers necessary hundreds or even thousands of design iterations can be calculated nearly simultaneously. Secondary flows develop in a heavily loaded NGV as a result of cross-passage pressure gradients and the slower moving flow in the boundary layer on the blade and walls. The same pressure gradient applied to the flow by blades in the boundary layers as they are in the rise stream zone. However, the fluid is turned more sharply and by the pressure gradient in boundary layer because it is moving more slowly there. So the so-called overturning is this. The flow rolls into a vortex where this more quickly rotating flows meet the blades, which is often directed to the suction side. An extremely quick fluid simulation code called VFAITH was created in order to have an effective optimization technique. Both the BFAITH software and the FAITH design system computed a linear flow fit solution by building an influence metric. A first-order finite difference approach is used to calculate these sensitivity metrics. The methodology of this research also include the CFD solver, design space, optimization problems, optimization strategy, genetic algorithm, simulation handling, sequential quadratic programming, and optimization setup. For the discussion of the result, it is commonly accepted that there is no one optimizer or even a class of optimizer that can be used to solve all types of engineering issues. It should be mentioned that each optimizer procedure comes with a wide range of possibilities. The outcome from the study shown here match those attained with the default settings. For example, the mutation rate in a SA or GA algorithm, the initially seeding, the random number of generator, and the initial state size can all be changed and perhaps tuned to give the best performance for the problem under consideration. Here, the downside is that the optimum optimizer may not have been used, that some element of chance may remain in process. On the other hand, starting from the same initial condition, the final result will always be the same. For the problem posed here, the design was always started from a base solution, and it is hoped that better design can be obtained close to the base geometry. This is mainly due to a lack of confidence that the loss predicted by the three-dimensional CFD code of comparable accuracy to the correlated loss prediction in the true flow codes, which was used to design the original two-dimensional section. The current CFD code assumes turbulent flow through the blade passage, whereas the real flow on the blade surface and the end wall is transitional. All the optimization jobs present here were run on a Sun Ultra 30 workstation. On average, every 100 iterations require on our CPU time for a 14 parameter design using a BFA IDH program. For the conclusion, in order to create a very effective design search and optimization technique, it has been taken advantage of the fact that linear flow response may be applied to a variety geometrical iteration that have already been demonstrated for turbine and compressor blades. The flow is compute using linear sensitive based on nonlinear flow calculation on per tube grids to reduce the significant processing time required for the optimizer. The optimized geometry comparison of linear and nonlinear outcomes show that such a technique is practical for use in three-dimensional design application. Using various optimization procedure, significant cost function reduction of the order of 30 to 50% has been accomplished. According to nonlinear data, cost function has increased by 10% from what was projected linearly. This holds true for both inverse and geometries that have been optimized based on linearly project flow variables. I think that's all from me. Thank you.